Okay, guys, so I'm gonna start to go over just moving forward with geometric series. We could start to write functions as power series or geometric series, so they look like specific functions now, which is a little confusing, but I'm gonna go over what a power series is and then trying to find an interval of convergence and the function that represents a given geometric series. So first thing I want to go over is what we did yesterday was we had a geometric series. Now one thing I'm starting with is I'm starting with n to be 0. So just keep in mind that this could change. It could be 1, then that if it was 1, right, I could do, and you would have the same series, because if you're plugging in 1, you just get r to the 0, which is 1 anyway, and you start with that first term that we had yesterday, a. But in this lesson, I'm gonna start with n to be 0 all the time just to stay consistent. Now, one thing that we have to get used to is for a geometric series, we have to make sure that that common ratio is between -1 and 1. This is called our interval of convergence. We have to get used to this. Like this or this notation is fine, but it both means interval of convergence. So meaning that those are the only values of r that are going to make this thing converge. If r was 2, it wouldn't work. If r was 5, it wouldn't work. Okay, so I'm going to move forward now, and now instead of using r, I'm going to do something a lot different. I'm going to say, let's have n go to n equals 0 to infinity. So we're taking the sum from 0 to infinity of a function x to the nth power, giving us this. You plug in 0, you get 1. Plug in 1, you get x. 2, you get x squared, and so on. And you're adding up all the terms infinitely. Now, same idea as above, right? Our interval of convergence, right? So again, this is considered interval of convergence, okay? X must be, just like what we did up here, but now we're talking about functions, X must be between -1 and 1, okay? If it's not between -1 and 1, it will work. If we have X to be 2, it's just not gonna work. Even if X was 1.5, it wouldn't work either. So, keep in mind that this is one of the important things on the AP test is we talk about interval of convergence. So now this is considered a power series, okay? A power series. Now what I want to talk real quick about the power series is that if you notice the way it looks here, we consider this centered at 0. Okay. What that means is, say, for example, you're looking at different functions and how we're going to represent them. So if I just look, I'm going to go back up here, right? Let's say we just look at this function here. And let me just rewrite it. Just to give you an idea of what I'm talking about here. All right, let's look at that function that I started with, n to be 0 to infinity, x of n. And you could see that you have okay. So I'm going to talk about partial sums. I'm going to talk about the first partial sum is 1, second partial sum is 2, third partial sum, the second partial sum, what am I talking about, is 1 plus x, then you have 1 plus x squared, and so on. And this continues. So hopefully let's see if we could see this. Can you see this? You can see it a little bit. All right. So let's say that we plug in those partial sums into our graphing calculator. Okay, so I have the first partial sum to be 1, the second partial sum to be 1 plus x, the third partial sum to be 1 plus x squared. 1 plus x squared. And if I hit graph, whoops, not that one. And if I hit graph, I wind up getting something that looks like that. Now, let's say I continue that and I do, let's do one more of these. The fourth partial sum would be 1 plus x squared plus x cubed. And here's the next one. If you notice, like say I zoom in at 0, right? Or zoom in at, just close to where all of those functions are near one another, right? So if you look how right now those first two all intersect at 0, 1, and then they continued. So because it's centered at 0, and let me draw this if you couldn't see it that well on the graphing calculator, is right, this was the first one, right? And then we know we have the next one is just a line, right? So this is like S sub 1, S sub 2, right? And then the other one goes a little bit lower, but it comes back up. And this is S sub 3. So when they say that it's centered at 0, it's almost like they're telling us that this is a pretty good estimate around the area when x is 0. After you go further than that, you could see how the functions start to gradually get further and further apart. So when we start to get really into it, we could use these to approximate, and we're going to do that in the next section, approximate values that are different. Like we did this with linear approximation. It's really the same idea, but now we could do a quadratic approximation, a cubic approximation, and so on. So this is really the start of it. But the idea that when a power function or a function is centered at 0, it just means that that's where our location will be, where it's a good estimate of the different types of functions that we're going to have. Okay? All right. Now let me go back to the lesson that we were talking about. So this one would be centered at 0. Now you could have it centered at a different place, right? So say it would be just written a little bit differently, where you have c sub n and then x minus a raised to the nth power. Now there's no real difference here. You still start with that first term. The difference is going to be that you have that a included into your sequence and series. Okay, and what this means is now that it's centered at x equals a, meaning that if we go back to the graphing calculator, right? If you go back to the graphing calculator, everything will be moved to whatever a is. If a was 1, this whole thing would be moved over 1 unit. If a was -1, it would be moved back to the left 1 unit, and so on. If it was at 5, say a was 5, you would have this whole thing moved at 5. But this would be good to estimate values closer to some value of a, whether it's 1, 2, 3, 4. Here we could estimate values that would be close to 0. We're going to get more into this as we go along. But what I want to do is now use this to try to represent some functions by a power series, okay? So here you would have find the interval of convergence. So that's very important because that's the only way that the function can converge, right? If we know what values we could plug in for x, we know when this thing would converge instead of diverge. Obviously, if I pick a value 2, right, that would be way too big. So I know it can't be bigger than 2, right? But let's be specific on what that is, and then let's use that to represent the geometric series, okay? All right, so in order to do that, right, number one, we have to come up with what is our common ratio, all right? Or like, what are we multiplying by over and over again, just like when we were doing geometric series. So what I'm going to do is rewrite this thing as 2x to the nth power. And you could see that that 2x would be my common ratio, what multiplying every single term by. Okay, so knowing that, I know that this common ratio has to be, absolute value of the common ratio has to be between -1 and 1. So when we're solving this, we go back to algebra 2, right? And you set up your inequality symbols. Okay, now with this, we could just divide everything by 2, and here would be my interval of convergence. Okay, so that's the first thing, interval of convergence, IOC, right? And now we want to find the function that represents this series, which is pretty easy because if we know, again, what my first term is, so you're plugging in 0, so 2x to the 0 is going to give me 1, and we already know my common ratio is 2x. So when I write this, I'm just using that same geometric formula, 1 over 1 minus r. So in our case, it'll be 1 over 1 minus 2x. And this would be the function that this series represents. So here is my interval of convergence, meaning I can only pick numbers between -1/2 and 1/2. Don't include them. And then my function that it represents would be 1 over 1 minus 2x. All right, let's go to the next one, same idea. Whenever you're given something like this with this alternating positive to negative, you got to include that in your common ratio. So for this one, our common ratio is going to be, well, you don't have to include it in the common ratio because it's absolute value, so my fault. But you will have to include it into the function. You'll see what I talk about in a second there, okay? Now, here, all right, when we look at this, the common ratio, besides it alternating back and forth, I know I want to have this to be, right, less than 1. Okay, so again, -1 less than x plus 1 is less than 1. And now we just solve. So if I subtract 1 to every side, or all, on the left, the right, and the middle, right, we get -2 is less than x is less than 0. Okay, so in this case, our interval of convergence would be -2 to 0. Now you could write it this way. That's interval notation. Like over here, we could write it this way as well. All right. It doesn't really matter which way you write it, but just notice on the AP test, multiple choice might have, actually, no more multiple choice. So it doesn't matter the way you write it. Just stay consistent on what you're doing. Now, this is where you need to include the negative sign, okay? Because this is included in your function. One thing that you could do, though, if you want, because they're both to the nth power, we could do negative of x plus 1 to the nth power. And then that way you could rearrange it where you have negative x, right, minus 1 would be, right, your your ratio for the geometric series. So again, your first term, ours is very easy. You plug in 0, you get 1, right? Our ratio is going to be this negative x minus 1. So now when we write our function, it's going to be, going back to the formula, 1 is our a, 1 minus negative x minus 1, which we simplified to 1 plus x plus 1, or 1 over 2 plus x, okay? Or x plus 2, whatever you guys prefer. Pretty good. Okay, 2 more for you guys, all right? And we'll do this again. So whenever I see something like this, and they're both raised to the n power, why not put them together, right? And it makes it a little bit easier to find what the common ratio would be, or what you're multiplying by over and over again. So here I'm going to do like a -1/2 times this x minus 3, everything raised to the nth power. So let's rearrange it. And I'm going to distribute that negative through, so I'll get 3 minus x over 2 to the nth power. Now this makes things a little bit easier. I know that this has to be between that -1 and 1 for my ratio. Now, in order to solve this, multiply everything by 2. Okay, subtract 3. Okay, and now when you divide everything by a -1, right, remember to reverse the symbols, right? So reverse the symbols. I'm going to actually flip the whole thing. This becomes 1 less than x, right, and less than 5. So my interval of convergence would be 1 to 5. Okay, and again, it doesn't matter which way you write this. Now, to look for the function, this is the ratio that we're using. Okay, our common ratio. Again, you're plugging in 0. So the function like a over 1 minus r. So I'm going to have 1 over 1 minus 3 minus x over 2. Remember my little tricks? Multiply everything by 2. Gets that to move away, right? And don't forget your parentheses here, right? Like I did, because you want to make sure the signs are all right. Okay, and then I would have 2 over 2 minus 3 plus x, or 2 over x minus 1. Okay, and that would be the function that represents that series. All right, last one that we have. Okay, this 3, now I put the constant out there on purpose. Don't use that. If that's not raised to the nth power, you do not need to worry about that. That would just be included in our first term when we go to that in a second. But now, here's our common ratio. We know that we want this to be between -1 and 1, multiply by 2, add 1, and there's our interval of convergence. And now, again, we want to go back to 1 minus r, a over 1 minus r. Our first term, now be careful, you plug this in, 0, but you do have that 3, okay? That 3 will still be there, and then it's 1 minus x minus 1 over 2. So again, let's multiply everything by 2. So I'll get 6 over 2 minus x, now distributing the same time, plus 1. So I get 6 over 3 minus x, and that would be the function that represents that series, that geometric series. Okay, any question? Oh, you can't answer questions because I'm not seeing you guys, but again, hopefully that helps, and I will see you guys shortly, hopefully. Thank you. Bye.